Hello class. So in this video, we'll continue on section 3.7, and we're talking about simple harmonic motion. In the previous videos, we went over a specific example of this. We're looking at this at a spring mass system under a couple assumptions. Right? So first of all, how did the system work? So we had a spring, right? We attached a spring to a rigid surface, and in our case, it was a ceiling. Right? And then what did we do is that we attached a weight to the spring, and then we let that weight stretch the spring out until it reached an equilibrium state, or an equilibrium position. Right? Then what we did is we gave it a pull. It doesn't have to be a pull. It could be a pull or a push on the weight. So either stretch or compress the spring past or below or after equilibrium position, and then you let go or give it a push, right? So it has some initial velocity. And then you see you see the motion of that weight as the spring starts expanding and contracting. And then when I talk about the position, remember that in my picture, it was where the spring, which is pictured in this case here, meets the weight. As I said, in other literature, they draw a difference. So here, the position of what we're looking at is a particle who's located where the spring is right at the middle of the weight, right? So in our picture, the particle we're looking at the position of is right here, where the spring meets the weight. And this picture is going to be at the middle of the weight. Okay? Also, this picture compared to ours, you would have to rotate this picture 90 degrees clockwise, right? Meaning that equilibrium position would be here, so right at 0. And then anything here would be below the equilibrium position for us, right? If you think of this as being vertical. And anything here would be above equilibrium position, right? So anything here would be positive position, anything here would be negative position. Okay? Now, we derived a differential equation that would model this motion, right? Specifically, whose solutions are the position functions of this particle as time goes by. Right? With t equals 0, it started when we let go of the weight or give it a push, after we stretch it or compress it, and then we see what's going on, right? As time goes by, what's the motion of the spring? And the differential equation we found, which was x double prime equals negative k over mx, right? Where k was the spring coefficient or the proportionality constant that came from the restoration force, right, which we got from Hooke's law, and m was just the mass of this object. Now, we derived that system with some assumptions. What were those assumptions? Well, we had 3. The first assumption is intrinsic in this model, meaning that we assume simple harmonic motion. What that means is that whatever medium we're working with, whether it's a spring, a string, or whatever medium it is, there's a restoration force. So whenever you stretch or compress that medium, there's a restoration force that wants to put it back into its equilibrium state. Okay? So that's why it's called simple harmonic motion instead of more general periodic motion. Right? But as I mentioned, this is a good example of periodic motion because it can be generalized. And you'll generalize it in more advanced courses. Okay? So that's the first assumption, simple harmonic motion. The second assumption is that we assumed no dampness. Right? So what was dampness? Dampness was, or no dampness meant that there was no loss of energy. Right? So dampness for us meant anything that would cause the system to lose energy. Right? So I gave examples of that. So friction of the spring mass system itself could make it lose energy. Right? Air resistance could make it lose energy. And then another example we're going to see is if we submerge this spring mass system under water, then the restoration force of the spring now also has to fight against the resistance force of water, right? So that's going to cause some energy to be lost to that process, right? So some energy in the system is going to be lost. Right? So those are 3 examples of what damping might look like. But again, for this particular model that we came up with, x double prime equals negative k over mx, we assume no damping, right? So there's no energy lost. So that was the second assumption. The third assumption was free vibrations or free oscillations. What that meant is that any oscillations that happen in our system are completely based on the restoration force of the spring and the weight of the object itself. Right? Compared to what? Well, an example of not having free vibrations is if we were forcing a specific pattern of oscillations on the spring mass system after we let go. Right? An example of that I gave was, let's say you let go of this and then you attach a robot arm. And that robot arm determines, for example, that our spring mass system is going to be oscillating between -1 and 1. Right? So that would be an example of a forced vibration on this system, and we wouldn't have free vibration. Okay? But again, in our differential equation that we derived, we assumed free vibration. Okay? So as a summary, the three assumptions were simple harmonic motion. The second one was no damping, right? So no energy lost. And then the third one was free vibrations or free oscillations, meaning that there's no forcing oscillations on this system. Now, before I start, so what I'm going to do here is I'm going to show you a picture or a simulation of what this motion looks like. Let me mention something about spring stiffness. Right? So again, this spring stiffness is our K, right? And then in class, I mentioned that K affects the oscillations of the system. Specifically, I don't know, I might have mentioned something different, but I might have mentioned in class that it affects the length of the oscillations, but I didn't specify how the lengths are affected. Right? So the length of the oscillation that is affected is actually the period, right? Meaning that the longer or the larger the spring stiffness or proportionality constant K is, the higher or the smaller, sorry, the period is going to be. Meaning that if we were to look at the graph of this motion, right, which I'm going to show you in this simulation, it's going to look like a sine function, and then the peaks, right, or valleys, those are going to be further apart, meaning that it takes longer for, closer together if the spring coefficient is larger, meaning that the peaks are closer together, right, which is equivalent to saying that the period is smaller, right? So remember that the period is how long it takes for a graph to repeat if the graph is periodic. Okay. So again, just to make that clear, the larger the spring stiffness is, which is our K in our differential equation, the smaller the period is going to be. So the mountains or valleys are going to be closer together. So it does affect the length of the oscillations, but it affects it horizontally instead of vertically, right? So I might have said nothing at all about what is affected, or I might have said that it affects it vertically. So if I did, I was probably thinking about thatness. So just forget about that. Just the larger K is, the smaller the period. So the closer or the smaller the oscillations are going to be horizontally, not vertically. Right? What's going to affect the verticality is going to be the dampness, among other things, like where we let go of the weight when we start the system. Okay. Just the only thing I wanted to clarify. Other than that, we're going to go ahead and see a simulation of this. So in the picture that I drew for the model, we pulled on the weight. So I'm going to do that here. I'm going to pull on it 2 units, right? So this is equilibrium position. I'm going to pull so that it's 2 units below equilibrium, right? So meaning here would start at a positive position at x equals 2, right? At t equals 0. And then what I'm going to do is I'm going to let it go. Now, there's a couple of things here that if you want, you can play with. You have the link for the website here. Now, the mass I just introduced, it's just the mass m in our system. So I just introduced a random number, so 1/2. Damping is 0, again, because we don't want any energy to be lost. And the stiffness, again, I just chose any random number. I chose k equals 2. And then that's it. We can just go ahead and play, and we'll see the motion in real time. Now, notice that this weight, or the position of this particle on the weight, keeps going all the way from -2 to -2 to 2. And in fact, this weight is just going to be oscillating between -2 and 2 infinitely. Why? Because there's no loss of energy, right? So there's nothing stopping this spring mass system to just be going back and forth between -2 and 2. Now, I can also see a graph of this, which you can see it here. Let me actually clear and start it again. Right? And again, you can see that it goes up all the way to a position of x equals 2, or a distance 2 below the equilibrium position, and it goes down all the way to -2, or a distance 2 above equilibrium position. So anything above is referring to stretching of the spring, and anything below is referring to contractions, right? Or, yeah, contractions of the spring. And here you can see that this is in fact a periodic function, right? And it has oscillations. In fact, we'll see when we find the general solution that, well, at first we're going to find the general solution as a linear combination of sine and cosine, but then we'll see that there's a formula to rewrite it as either a single sine function or a single cosine function. Right? So it makes sense because what's being graphed here are the solutions to the differential equation under these specific parameters. Now, here we started with an initial condition of x of 0 equals 2, meaning that at time 0, we started 2 units past equilibrium. In this particular model, we're assuming an initial velocity of 0, meaning that we just let go of the weight instead of giving it a push, for example, when we let go. So under those initial conditions, we can solve for our coefficients, and we can get an explicit or particular solution for an ODE. And this is what it looks like. Now, let's see what happens. Let me restart this. Let's see what happens if we increase the stiffness. And again, remember, increasing the stiffness means that the period is decreased, right? Meaning that however far apart those mountains or valleys are in the graph that we saw, those become closer and closer and closer together. Okay. So if you take in trig, you know what periodicity is. I'm just explaining it that way if you don't remember how it works. Right? So let's increase this from 2 to 5, and let's see how it looks like. Now, one thing you notice here, again, as I mentioned, there's no difference in the vertical motion, meaning that it goes from -2 to 2, independent of the stiffness. But here you can see that the spring is moving faster. Right? In the graph, that's going to correspond to a smaller period, meaning that, as you can see here, the mountains are closer together. So the peaks are closer together, and the valleys, or the bottom of the valleys, are closer together. Right? So it's a smaller period, or you can think of it as a higher frequency. So if you're taking trig, you know what frequency is. It's the number of cycles completed per unit of time. Right? So we get a higher frequency. So I'm going to clear this again because it's showing 2 graphs. And we can play a little bit more. Let's say, what if we increase this all the way to 10? And then let's see what happens. It's probably going to go pretty fast. Yeah, so you see it's going faster, right? And then if we look at the graph, again, you can see that the peaks and valleys are closer together, meaning that the period is smaller or the frequency is high, right? So again, the higher the proportionality constant K or stiffness, spring stiffness K, the smaller the period. And again, you can play with this if you want. You can introduce dampness, for example. So let me show you what happens if we introduce dampness. Oops, I want to go back to 2. Say I'm introduce a dampness of, say, 1 at first. And let's see what happens. Right. Now you see that there was a loss of energy, right? Meaning that it eventually went back to its equilibrium state, right? Because there's no more energy in the system. Because again, when we pull here, there's potential energy. It's potential energy, and then when we let go, that potential energy becomes active, right? And then it starts oscillating. But if there's energy being lost because there's damping, then we get the situation, right, where energy is lost, and then our system goes back to equilibrium. So we don't get infinite oscillations like in the previous case. So that's the difference. When you include damping, there's energy being lost, right? So that we get the situation. So this is as good as a picture as I can show you. Actually, let's see a graph, see how it looks like. So let me do it smaller, so it takes a little bit longer. It's 2.5. Restart this. I'm going to press play and go immediately to the graph. And you see the motion. It starts at 2, but then we're losing energy, so the oscillations become smaller and smaller and smaller and smaller and infinitely smaller until we basically reach equilibrium position, right? And there we go. And then I say basically because what's happening is that as a limiting process, as t approaches infinity, this is approaching equilibrium. But we'll see that in the solutions when we talk about the damping case. Now, unfortunately, in this case, I don't think I can play with forcing on the oscillations, right? So if we don't say that we have free vibrations, but at least for these 2 cases, when we have damping and when we don't have damping, you can see what happens, right? Okay. So that's all I'm going to do with this. I just wanted to show you how this looks like because there's only so much I can do with pictures, right? I think this gives you a clearer picture of what is going on.